faithfully conveying value and interpreting the best books from around the world. Hello, this is Sally's Book Talk. Today we'll be interpreting the book Hormones, a little history. What are hormones? Hormones are small molecular substances inside animals like insulin, adrenaline, and so on. They're secreted by specific glands, transported through the blood to various parts of the body, act on specific cells and organs, and produce specific effects, thus influencing development and behavior. The science that studies hormones is called endocrinology. The amount of hormones in humans is minuscule. For a long time, they were unknown, yet silently influenced human life, shaped destiny, from appetite to sexual desire, from anger to care, all tied to hormones. So, understanding hormones helps us rediscover ourselves. The authors, Randy Hutter and Epstein, are medical doctors and writers in residence at Yale University School of Medicine, guiding students in thesis and science writing, often publishing works like Hormones in platforms such as the New York Times. The book, A Little History, was rated the most popular of 2018 by Science News magazine, making it the go-to read for understanding hormones. The authors outline the origins and development of hormone research, describing some fascinating anecdotes and unusual events. From insulin to thyroxine, from sex hormones to oxytocin, and so on. The research process for each hormone is impressive, filled with setbacks and lies, sometimes even laughable. But ultimately, hormone research has achieved great accomplishments. Today, endocrinology has become one of the most remarkable biological sciences. Following the historical thread of hormone research, we'll interpret this book from 4 aspects. First, how are hormones discovered? Second, how did hormone research go astray? Third, how to dose hormones. Fourth, what are the mechanisms of action for different hormones? First, let's talk about the first question. How were hormones discovered? The 19th century was a miraculous era in science history. Darwin proposed the shocking theory of evolution, and Koch proposed the germ theory. At the same time, research on hormones was quietly unfolding. In 1848, German doctor Arnold Berthold kept 6 roosters in his backyard.
Not to make roast chicken, but to conduct experiments.
Berthold used roosters for the experiment because he targeted their 2 testes. But back then, people had noticed simple tissue blocks in the human body called glands. Though structurally simple, their functions were unclear, like the thyroid, and folks were eager to figure out what these glands actually did. As a representative gland, testes became the research focus, probably because they only exist in males, sparking more curiosity. Before Berthold, people could only speculate about testicular functions. And Berthold was the first to seek answers through experiments, pioneering hormone research. Frankly, Berthold's experiment wasn't complicated. He divided 6 roosters into 3 pairs, removed both testes from the first pair and both from the second pair. The third pair was trickier. He removed both testes, then transplanted 1 testis into the other rooster. Thus, each rooster ended up with 1 testis, each from the other. Berthold then raised the roosters, waiting and observing quietly. The results were fascinating. Fully castrated roosters acted like hens, lethargic with faded combs, losing interest in hens. Those with 1 testis behaved normally, proving even 1 worked.
But the third pair, with swapped testes, yielded surprises.
Initially, Berthold transplanted the testes not to their original spot, but between the intestines. Turns out the wrong location didn't affect the testes' function. Both roosters thrived, remained spirited, and still fantasized about hens. Berthold had theorized testes sent commands via nerves to influence behavior, but when he examined their intestines, he found no new nerve connections, only blood vessels.
Thus, Berthold deduced the testes must produce some substance.
These substances, like arrows shot from testes, traveled via blood throughout the body. Though this experiment proved hormones' existence, it was overlooked at the time. Half a century later, William Bayliss, a physiology professor at the University of London, and his colleagues conducted experiments on dogs, proving Berthold's hypothesis. And hormone theory was finally accepted by the scientific community. Bayliss believed all glands, whether testes, pancreas, or adrenal glands, had similar working mechanisms. They weren't independent but part of an organic system. And we now know that's the endocrine system, but the concept didn't exist back then. Bayliss wanted to prove this idea and decided to use dogs for experiments. Bayliss's research target was the pancreas, which is closely tied to digestion. When dogs eat, the pancreas secretes digestive fluid into the tract. Bayliss wondered how eating affects pancreatic activity. His approach was to surgically cut nerves around the pancreas in dogs, then observe if feeding impacted digestive fluid secretion. Results showed that severing nerves didn't affect the pancreas's secretion function. This implied that, since the pancreas got no nerve signals, it must receive other signals. This signal was a small molecular substance, later named secretin, the first hormone isolated. However, this view clashed directly with Soviet biologist Pavlov's conditioned reflex theory. At that time, Pavlov's conditioned reflex experiments on dogs were famous worldwide, with reflexes relying on nerve transmission. Pavlov thought pancreatic secretion must result from nerve control, so he fiercely opposed Bayliss's view. Only after Bayliss used rigorous experiments to rule out nerve interference did Pavlov have to accept this fact. Even so, Pavlov still held a grudge. Thus, he missed the boat on hormone research. Fortunately, Bayliss didn't stop there. He and colleagues further suggested complex interactions between many organs, like the digestive tract and pancreas. For example, between uterus and breasts, brain and heart, etc. Some interactions happen via nerves, others through small molecular chemicals, a view largely matching birth holds from half a century earlier. Under great pressure, they continued animal experiments, confirming this idea, and in 1905, formally named these small molecular substances hormones. The finalization of the term hormone marked the birth of endocrinology. As a groundbreaking biological discovery, hormones rapidly gained public attention, sparking waves of research that included myths exaggerating their effects. End quote. Some legends were even both laughable and frustrating. That brings us to our second question. How did hormone research go astray? Amid the surging hormone research wave, many were actually profiteering in chaos, eventually becoming typical charlatans. Some, though not intending deception, sounded like they were earnestly spouting nonsense. For instance, psychoendocrinologist Louis Berman believed hormones could create an ideal society where everyone maintained chemical balance, no sin, no obesity, no ignorance, all solvable by hormones. Amid the chaos, some scholars persisted, conducting in-depth hormone research and soon discovering new hormones like cortisol and adrenaline. Sex hormone research, however, was full of twists, sparking controversy still discussed today, with the story again focusing on testes. Driven by vague beliefs, some sought powerful strength from testes.
French physiologist Charles-Édouard Brown-Séquard pioneered this, astonishingly experimenting on himself at age 7.
He collected testicular secretions from guinea pigs and dogs, mixed them, injected himself, then claimed enhanced libido, longer urination range, and feeling 30 years younger.
This caused quite a stir, with many imitating Brown-Séquard's methods. Yet just 5 years later, the frenzy abruptly died when Brown-Séquard passed away at 76. While not premature, it fell short of the expected longevity, dealing a heavy blow to believers in testicular magic. Thus, Brown-Séquard's therapy faded, but interest in testes persisted. Around 1920, a new therapy quietly emerged. Some performed complex surgeries, transplanting ape testes into men, claiming enhanced masculinity. Others sold goats specifically, not for soup, but for testicle transplants, where clients chose goats, then had testes removed and transplanted in kitchen surgeries. The operators needed zero medical knowledge, just a medical facade and the guts to cut to make a fortune. Amid this circus, Austrian physiologist Eugen Steinach differed from those frauds. He was a renowned Vienna doctor who designed rigorous experiments. Steinach didn't initially believe testicular myths. He just wanted to answer, Can hormones influence human behavior? Are behavioral differences between men and women determined by hormones? To solve this mystery, he conducted rat studies proving the brain affects hormone secretion, and hormones conversely affect brain activity. Building on this, Steinach published extensively, got 11 Nobel nominations, never won, but became famous enough to push a wild idea. Since hormones affect the brain, why not use testosterone to stimulate it? From 1920, Steinach promoted his human renewal plan, vasectomies to trap semen like traffic, boosting libido, intelligence, and reversing aging. This wild plan went viral. Steinach even became a verb meaning to gain vitality via vasectomy. Many believers, including celebrities, got vasectomies, but Steinach himself abstained. Not that he doubted his plan, he was just too old, likely lacking sperm to store. So he opted out.
Today, Steinach's scheme is debunked. Research shows vasectomies cause only short-term testosterone bumps with negligible long-term effects.
Those reporting dramatic results were mostly placebo-affected, psychological cues making them feel better. Still, Steinach's work proved the hormone-brain link, upgrading endocrinology's foundations. And the upgrade's key? Hormone dosage. The biggest challenge in early hormone research was that hormones were incredibly scarce. Scientists had to find a way to measure them, or research couldn't advance. So now, let's talk about how to measure hormone levels. Cretinism is a classic hormone deficiency disease causing stunted growth and intellectual disability, once synonymous with idiocy. Over a century ago, doctors knew it was due to insufficient thyroxine secretion. Thyroxine is secreted by the thyroid gland and, like growth hormone, promotes body growth. The difference is, growth hormone comes from the pituitary gland. Deficiency causes dwarfism, not cretinism. Back then, doctors knew how to treat cretinism. The method was simple. Take thyroxine medication, easy to use and cheap. So cretinism should have been curable long ago.
Yet, that's not the case. Many new cases pop up yearly because infants seem perfectly healthy at birth.
But symptoms only show after 6 months. By then, it's too late. Brain damage from thyroxine lack is irreversible, so early detection and treatment are key. However, early detection isn't easy. That brings us to hormone research's core problem: how to measure it. Since hormone levels in humans are super low, it was once thought impossible to measure. At the time, doctors had no better way than watching symptoms to gauge thyroxine levels. They just waited for symptoms to treat. This led to many tragedies.
Accurate hormone measurement became an urgent priority for research.
Then, a remarkable American woman stepped onto the science stage. Rosalind. Though Rosalind Yallow's name isn't as famous as others, her hormone measurement technique was crucial for modern biomedicine. In 1950, Rosalind worked at the VA's nuclear medicine department, setting up a lab for tedious research, and accidentally uncovered key hormone clues. Back then, people thought hormones were too scarce to trigger immune reactions, meaning the body wouldn't reject them, so hormone therapies didn't consider immune risks.
But Rosalind and colleagues discovered the body sometimes produces antibodies against foreign hormones like insulin. A radical finding, contradicting mainstream views.
Their paper faced hurdles getting published and received little attention. Fortunately, Rosalind valued her research, believing hormone immune reactions could measure hormone levels. Once this idea emerged, Rosalind immediately designed extensive experiments with colleagues to test its feasibility. Turns out, they were right. Let's use insulin to explain Rosalind's method. Insulin is a protein hormone. Drawing blood contains trace amounts, but how do we measure it among countless chemicals? Exactly how much insulin is present. Insulin's trait. When injected into animals, it produces specific antibodies. Insulin and antibodies bind specifically. Rosalind used this. She prepared radioactively tagged insulin standards, combined them with antibodies to create a measuring ruler. And then,
Adding blood samples to this solution makes blood insulin compete with radioactive insulin for antibody binding spots.
imagine musical chairs. Antibodies are chairs. Blood insulin wears red shirts. Radioactive insulin wears yellow. both competing for seats. Suppose one yellow shirt per chair. When red shirts join, some yellow shirts get bumped off. Counting displaced yellow shirts reveals how many red shirts claim chairs. Similarly, measuring free radioactive insulin changes lets formulas calculate blood insulin levels. This is radioimmunoassay. The technique is not only fast and simple, but also incredibly sensitive, accurate down to per milliliter. 1/1000th of a gram, now a vital tool for studying trace chemicals. Since radioimmunoassay emerged, global cretinism cases plummeted as doctors could easily measure thyroxine levels, earning Rosalind the 1977 Nobel Prize in Physiology or Medicine. Notably, Rosalind waived the patent to lower thyroxine testing costs, ensuring more cretinism patients received timely treatment. With such convenient, accurate hormone measurement tech, endocrine research soared, quickly yielding major breakthroughs. Now, next, researchers naturally wanted to know how hormones actually work in the body. Finally, let's discuss hormone mechanisms of action. As hormone research deepened, understanding of their functions expanded, fueling high hopes for hormone therapies. Hormones could offer precise solutions like antibiotics for disease treatment. But truth is, many hormones remain mysterious. Even when discovered, their mechanisms are unclear, as with oxytocin and leptin research. In 1948, a medical team noted something fascinating. Intense uterine contractions coincided with milk dripping from nipples. They speculated the hormone triggering contractions might also stimulate milk secretion. Further analysis confirmed this theory. In 1953, this hormone was purified and named oxytocin, Greek for quick birth. Just 2 years later, the research won a Nobel Prize. Such speed was rare, showing immense excitement about oxytocin. Around the same time, other scientists found maternal bonding has a critical window. Miss it, and mother-offspring become strangers. If a lamb was taken right after birth and returned just 5 minutes later, the E would reject it, even butting it away. Researchers speculated a hormone might control maternal affection. Later research confirmed that was indeed oxytocin.
Suddenly, oxytocin became famous as the love hormone.
Many passionately promoted oxytocin, even through famous TED Talks featuring dedicated presentations. One speaker chatted with the audience while spraying oxytocin up his nose. He claimed this created feelings of love and empathy with strangers. But recent studies show oxytocin's mechanisms are complex, can build trust or suspicion, foster love or jealousy, linked to empathy and racism. These contradictory results baffle researchers. Current consensus: oxytocin doesn't create specific feelings, it amplifies existing ones, good or bad. In short, oxytocin seems to have no special behavioral impact, though linked to love or sex, drug development is distant due to complexity. Some hormone drugs only work when deficiency is clinically confirmed, useless for healthy people, like rain nourishing life in a dried-up lake bed.
But if the lake's full, one more drop means nothing.
Leptin research faces similar issues. Some crave drugs to eat endlessly without gaining weight. Leptin once seemed their salvation. Since the 1950s, researchers suspected obesity linked to hormones. One experiment showed mice eating uncontrollably after partial hypothalamus removal. No restraint whatsoever. Researchers hypothesized the hypothalamus relates to appetite-controlling hormones. Leptin was later discovered, literally thin hormone, inducing fullness to curb eating. Without leptin, fullness rarely occurs, leading to insatiable eating and inevitable weight gain. So, can leptin be used for weight loss? This requires understanding leptin's mechanism. It's an alarm system monitoring energy levels, triggering fullness when sufficient. When energy is insufficient, leptin levels drop, triggering hunger that drives the body to consume more food. During food scarcity or extreme dieting, persistent hunger keeps leptin low, disrupting hypothalamic hormone release and interfering with development.
Simply put, energy deficiency downgrades bodily functions, sometimes causing premature menopause in women.
Still, leptin isn't a savior for obese individuals.
Obesity stems from multiple factors. Leptin is just one component whose levels fluctuate with energy supply, making direct weight loss use difficult.
Crucially, leptin influences other hormones, creating ripple effects throughout the system. Ironically, weight loss attempts might even trigger diabetes. In short, leptin's mechanism is far more complex than imagined. Like oxytocin, it operates in a nonlinear hormonal network where interactions alter outcomes, unlike predictable domino effects. And these intricate cause-effect relationships remain incompletely understood. Regardless, through scholars' collaborative efforts, new insights continually emerge. We now recognize the hormonal network's existence and grasp its macro-level dynamics. All setbacks and failures have become stepping stones to progress. All exploration and effort have yielded corresponding rewards. In specific contexts, hormones control our height, influence our weight, and even sway our loves and hates. But humans refuse to be slaves to hormones. We aim to master them. Perhaps future hormone-based drugs will benefit humanity like insulin does for diabetes. That's the inspiring story of hormone research. Okay, that concludes our interpretation of a little history of hormones. Reading notes are below the audio. See you next time.